People like to talk about thalidomide as an example of why stereochemistry is important, but a little more real-world example would be ibuprofen, which in most drugs comes as a racemic mixture, which is a mixture of two stereoisomers. It's two enantiomers. One of these reduces pain, the other does not. How do we tell them apart? We need a way to identify which enantiomer is which. And we've come up with a way of doing just that, and it's known as the RS naming convention. So, we can examine a molecule, and we can examine how its atoms are arranged in space, examine the configuration, and we can give it a name. We can determine which of these is which stereoisomer. So, we look here, we find our stereogenic center in our 2-butanol, and step 1 is to assign priorities to these different groups attached to the stereogenic center. Priorities, it's just you're giving them each number. There's 1, 2, 3, and 4 on an sp3 carbon. And the higher priority goes to the atom with the higher atomic number. So, for example, oxygen would be higher priority than carbon. So, let's draw a close-up view of what we just had there at this stereogenic center. We have a methyl group, an ethyl group, a hydrogen, and a hydroxyl group. So we can look at this immediately. We can see this oxygen. That's number 1. That's highest priority. 2 is the ethyl. 3 is the methyl. 4, of course, is hydrogen. So how did we come to decide what 2 and 3 were? Now, let's draw this back up here. We decided 2 and 3 because if the first atom of 2 groups is the same atom, so we have 2 carbons, you look at the next attachment. So in our ethyl group, we have carbon, 2 hydrogens, but another carbon, whereas in our methyl group, it's just 3 hydrogens. So ethyl higher priority than methyl. And finally, if we were dealing with an alkene, or something with a double bond counts as 2 bonds to that same atom. So we can look at an example of this simple alkene right here. We'd spread it out as if it were bonded to 2 carbons, just like this. We have one of those bonds here and the other right here. So step 1, assign our priority groups, priorities. Step 2 then is to arrange these groups, or I guess really rotate the molecule because we can't just shift groups around or else that's a different stereoisomer. We're going to rotate this molecule so that our lowest priority group is facing away from us. That's this dotted line, which we've already done that, but let's say we hadn't. Let's draw this upside down here with this hydroxyl group facing away, hydrogen facing towards us. And we know that our hydrogen is our lowest priority group. We need that backwards, so we need to flip this upwards. And we end up with what we started with. So we're in good shape. So step 2 then, after number 1 priorities, step 2 is we put our lowest priority group away from us. Moving on to step 3. We're going to take these priority groups and we're going to connect the dots. What I mean is, let's draw this back up here, hydroxyl, hydrogen, assign these groups back here, and we're going to connect these. And since we already sort of took care of our lowest priority group, we're just going to connect 1 through 3. We sort of banished number 4. So connect the dots 1 through 3. And we're going to look at the direction of this arrow. This circle we drew. If we drew it going to the right or clockwise, that's going to be R. We're going to name that R, which stands for rectus, which is Latin for right. And on the other hand, if we're going to the left or counterclockwise, it's going to be S, sinister, Latin for left. So we look at our molecule here, going to the right, rectus, that's R. We connect these in our example, and we end up with R2-butanol. That is the name of this stereoisomer of 2-butanol. Let's look at another one. So let's put this hydroxyl group away in this configuration here. So what do? Step 1, priorities. We know these, 1, 2, 3, 4. Step 2, put that hydrogen away. So this time we need to flip it down because we're not set up right. And now we have our hydroxyl forward, hydrogen backwards. Let's write these priorities in here. And step 3, connect the dots. Okay, arrow going to the left, counterclockwise. That's going to be S, or sinister. So this stereoisomer is S2-butanol. Well, that's fine. I think we can handle that. But what do we do if there are more than one stereogenic center in a molecule? So let's take a look at this here. We have a pentane, hydroxyl group here, and here. 2,3-dihydroxypentane. So we're just going to treat these separately. Treat each center just like we did on the other ones. So step 1 on this one, 1, 2, 3, 4. 4 being the hydrogen facing away. It is going clockwise and coming down here. Assign these groups. Let's take a closer look at this one. So we have our carbon attached to our hydroxyl, to hydrogen, of course to our ethyl group, and over here to our remaining part of the molecule. So we have 2 carbons here. What do? Look at the next molecule. We have an oxygen attached here and a carbon there. So obviously this is the higher priority group. And this one is going clockwise as well. So clockwise and clockwise to rectus, R and R. So this molecule is RR, 2,3-dihydroxypentane. And that's the RS naming system.